Welcome back to this lecture on the growth of functions. In the second segment, we will define the big O notation. Let f and g be two functions. These are numerical functions. That is, their domain is the set of real numbers or a subset thereof, and their codomain is also the real numbers. We say that f of x is big O of g of x, written with g of x in parentheses after the big O, if there exist two constants c and k such that the following constraint holds. And I'm going to build up this constraint step by step. So first we start with f of x, and we take the absolute value of that. Remember, the absolute value of a number is the same number if that number is positive, or it drops the sign of the number if the number is negative. So the absolute value of minus 5 is 5, the absolute value of 0 is 0, and the absolute value of 5 is also 5. So we take the absolute value of f and the absolute value of g of x, and the constraint here is that the first one is less than or equal to the second one after you multiply the second one by the constant c. Now the problem in this definition so far is that the value of x is unspecified. In logic, x is a free variable here. So this relationship must hold for every value of x such that x is greater than some constant k. And that is the definition of the big O notation. So intuitively, what this definition means is that if you ignore the absolute values and the constant c, it says that the value of f of x is always less than or equal to the value of g of x, as long as x is large enough. Remember, we are focusing on the end behavior of the functions. So in particular, what it means is that the function g of x grows faster or is always larger than a function f of x if you look far enough on the right in the graph of the functions. So let's try to illustrate this definition with some graphs. So the x-axis is going to be x. Now, please be aware that this definition here has nothing to do with algorithm complexity. It applies to any numerical functions f and g. But to illustrate the meaning of this definition, I'm going to assume that x means specifically the size of the input to the algorithm, since the function f and g are going to represent the time complexity of some algorithms. So x is on the horizontal axis, that's the input size. The y-axis is f of x or g of x, that's the runtime of the algorithm. And let's draw an arbitrary function g of x and an arbitrary function f of x. Now, we're not comparing directly f of x and g of x. We're going to compare f of x with the function g of x multiplied by constant. So now I'm going to draw as a dotted line the function c times g of x for some constant c. And in this case, what you notice is that starting at 0 for x up to about this point, c times g of x is below f of x. In other words, c times g of x is less than f of x. So we don't have this property here. But the good news is that starting at this point, going to the right, c of g of x appears to be always larger than f of x, or above f of x in the graph. So we're going to take this point down here as the value for the constant k. And if this graph is correct, what we can conclude is that it is always true that c times g of x is above or is larger than f of x, as long as x is strictly greater than k. And therefore we can infer from that property that it is true that f of x is big O of g of x. So now let me make a few comments on this definition. First, the constants c and k are called the witnesses of this big O relationship. So if you have two algorithms whose runtimes are f and g, how do you prove that f of x is big O of g of x? Well, to prove such a relationship, you must find the two constants or the two witnesses, c and k, and then prove that this relationship holds given the specific values you picked for c and k. So let's rewrite this constraint in logic so we clearly understand what the meaning of that definition is. The definition says that for f of x to be big O of g of x, there must exist two constants or two witnesses c and k. So in predicate logic, what that means is there exists c and there exists k, such that this property holds for all values of x that are big enough. So it must be the case that given c and k, for all x, if x is greater than k, that's this part of the definition, then this inequality holds. That's the conclusion of the conditional. So make sure you convince yourself that this compound proposition of predicate logic is indeed an exact translation of this definition in logic. Now, you're all familiar with quantifiers. X greater than k is simply the greater than predicate. Let's call it P. So it's P of x and k. And this is a slightly more complex predicate that given x and c takes f of x, g of x, then the absolute values, and then compare one to c times the other. So we have two predicates, P and Q. We have a conditional. We have quantifiers. There's nothing new here in terms of logic. Make sure you get very comfortable with this formula of predicate logic, as we will be using it a lot when we are trying to prove big O relationships. From now on in this course, when using the big O notation, we are always going to assume that x is positive and that f of x and g of x are also positive. Now, why is that? Well, remember, I already mentioned that this definition applies to any numerical functions. But we will only be interested in functions that represent the time complexity of algorithms. So for us, x is going to always be the size of the input, which does not make sense as a negative number. And f of x is always the runtime or the time complexity of the algorithm, which also doesn't make sense as a negative number. And by the way, that is the reason why I drew the graph as I did over here. So notice in particular, I never considered negative values for the input x, and I never considered negative values for the y-axis, or the runtime. Notice also I only drew the graph in the first quadrant. I didn't consider what happened on the other three quadrants. And as a result, I didn't need to draw the absolute value function here on any of these functions, since the absolute value of a positive number is exactly equal to that number. So that's the reason why we're making these simplifying assumptions, and we will never bother with the absolute values in the rest of the course when using the big O notation. So let me conclude this segment by bringing up some terminology issues. Another way to state that f of x is big O of g of x that you'll see in some textbooks or on the web is to state that f of x is equal to big O of g of x. Now that doesn't make too much sense, but that's a common notation. Another way of saying it is that f of x is a member of big O of g of x. Now this makes more sense because if you think as big O of g of x as the class or the set of all functions that have that property, then it makes sense to say that since f of x has that property, it is a member of the set of all the functions that are big O of g of x. Now, these three common notations are really mathematical. Sometimes you just want to state the relationship in a more informal way, and let me mention three different ways of doing that. The first one is to say that f of x does not grow faster than g of x. This is pretty much understood by looking at the graph of the functions. Remember, the whole point of the relationship is to state that f of x is always below g of x. Now, of course, that's only true after you multiply by a constant c. So one way to say that in English is up to a multiplicative factor. But the point is that f of x does not grow any faster than c times g of x, because f of x, starting for some value of x equal to k and higher, f of x is always below c times g of x. So it doesn't grow as fast as c times g of x. It grows slower. That's what the big O relationship means. Another way of saying that is to state that c times g, which is a function, is an upper bound for the function f. An upper bound means it's a value that's larger than what you're comparing it to. So here it's saying that c times g is an upper bound for f. And here, again, the assumption is for large enough values of x. But that's not usually stated. That's understood or implied. And the last way I want you to think about this relationship, which is very common, is to say that g dominates f. Meaning, again, g is an upper bound or is larger than f. But this is only true for large values of x. And so the word that is usually used for that is asymptotically. Meaning when x grows large enough or goes toward plus infinity. So g dominates f is a simple way of thinking about this relationship. F of x is big O of g of x.